Hey Gr10s, welcome to term 2. I hope you had an awesome holiday despite the lockdown and that you are refreshed and ready to work hard during online teaching in term 2. So last term we finished off with waves, and waves is a very broad topic, and obviously you get different types of waves. For example, sound waves, light is a form of waves which we're going to talk about today. What else? Sound is another form of wave. So when we talk about sound doesn't need a medium in which to travel. If you have a bell in a jar and you remove all the air from that jar, you won't actually hear the sound because there is no medium through which the sound can travel. So sound travels at a speed of about 1,000 kilometers an hour in air, but it'll travel much faster in a liquid that's a more dense medium, and even faster in a solid. When we talk about electromagnetic radiation, we say that it's self-propagating because it doesn't need a medium to travel. So electromagnetic spectrum is made up of electric waves and magnetic waves. So EM stands for electromagnetic, and obviously then electromagnetic we've got an electric wave, and we've also got a magnetic wave. Okay. So if you've got an accelerating charge, a charge that's moving faster and faster, it can be a source of an electromagnetic wave. So a charge has got an electric field around it. You learned about charges having electric fields last year. And if you've got an oscillating charge, so a charge that's moving, it will cause an oscillating electric field. By induction, an electric field induces a magnetic field in the plane perpendicular to itself. So what that means is if you've got an electric field, notice how the electric field is a wave that's going up and down, oscillating in the vertical plane. So I'm going to trace over it. Notice how the electric wave is in the vertical plane. Okay. At the same time, we've got a magnetic wave. Now this magnetic wave is actually going back and forth, oscillating in the horizontal plane. So if you've got two waves, one in the vertical, one in the horizontal, and they're moving at right angles to each other, you can say that the angle between them then is perpendicular. So let's have a look here. It's over there, they're perpendicular. This vertical wave is perpendicular to that wave. If you were to measure that angle is 90 degrees. Right, so we say that the changing magnetic field induces an electric field. So if you've got a changing magnetic field, it's going to induce an electric field. The electric field is going to induce a magnetic field. The magnetic field is going to induce the electric field. The electric field is going to induce a magnetic field. The magnetic field is going to induce an electric field, and so on. So that's why the one induces the other, and that's why we can say that electromagnetic waves are self-propagating. They propel themselves, and that's why electromagnetic waves, radio waves is an example, light is another, Wi-Fi is another. They do not require a medium to travel. They're self-propagating. Maybe just add that as a little note. Therefore, do not a medium is a substance. Okay, so electromagnetic waves. Electromagnetic radiation is a type of wave. It's got an electric wave and a magnetic wave. The one induces the other, so the electric wave induces the magnetic wave and so on, and that's why we say that they're self-propagating. So the videos that I'm going to upload to Teams are going to talk more about the characteristics of light in the EM spectrum. So the EM spectrum, we've got a spectrum is a range, and it ranges from long wave radiation. So please make a little note here that this side is long wavelength, because a radio wave that's got a wavelength of 10 to the power of 3 meters, so 10,000 meters, is much longer than a gamma wave or a gamma ray wave, which has got a wavelength of 10 to the minus 12. So obviously that's picometers, much smaller than 10,000 meters. So on this side you can make a little note that this is short wavelength. And you can see that the length from a crest to a crest here is much longer than from a crest to a crest over there. So that's short wave, whereas over here that is long wave. Okay, so that's wavelength. Now let's talk about frequency. So the frequency of a long wave, if you've got a very long wave, it's going to have a very low frequency. Because it takes so long to get a wave, you're not going to have many waves in a certain amount of time. So remember, frequency is how many oscillations you see per second. So long wave radiation, you're going to have a very low frequency. Whereas if you've got very short waves, you can have a lot of those waves in a second. And that's why we say that this is in high frequency. Okay, so low frequency, high frequency. Notice that there's this inverse relationship between wavelength and frequency. Long wavelength, low frequency, short wavelength, high frequency. Please make sure that you understand the difference between them. So opposite relation between those two. Okay, so low frequency, opposite end to short wave. And I've just explained why. Let's have a look at it in terms of mathematical formula though. Before I go on to that, I want you to please know I'm going to be uploading some videos. They will explain to you where gamma rays are used, where X-rays are used, and so on. So on page 2, I want you to just write a little note of the uses, where they're useful in everyday life, or in real life, not necessarily everyday life. So where would you use gamma rays, where would you use X-rays, why they're useful. Also, before I continue, I want to highlight that there's a very narrow band in the nanometer range, and that we call visible light. So remember, nanometer is 10 to the power of minus 9. So infrared light has got a wavelength of 10 to the minus 5 meters. Ultraviolet has got a wavelength of 10 to the minus 8 meters, and visible light is in the region of about 10 to the power of minus 9 in the nanometer range. So this narrow band, that we call visible light. So visible light, you can see the longest wavelength that you get is red light, and violet light, or purple light, is the shortest wavelength that you can see. And that, like I said, is in the nanometer range. Beyond red, we say that it's infrared. So if the wavelength is longer than red, it's infrared. If it's shorter than purple, then we say that it's ultraviolet. So ultraviolet's over here, UV, and this is then beyond red, we call infrared. Okay. It also gives you a size that wavelength with a length of 10 to the power of 3 meters would be actually longer than buildings, unless it's one of those super tall buildings, but kilometers long, whereas X-rays are much shorter. So please make a little note that your research assignment will be to watch the videos, and from the videos then to make little notes on where you'll find gamma rays, X-rays, UV, visible, infrared, microwave, and radio waves. So all of these are just types of electromagnetic radiation, and they fit onto the EM spectrum. So this we call an EM spectrum because it's the range from long wavelength to short wavelength, or low frequency to all the way up to high frequency. It's on a spectrum. Right, let's look at some formula. So we've got this first formula, E is equal to HF. E is energy measured in joules. H is Planck's constant, 6,6 times 10 to the minus 34 joules per second. It's a constant. We will give you that value in tests and exams. And F is, you know that already from the last section of work, frequency. Frequency is measured in hertz. If you make a magic triangle out of it, E is on the top, H on the bottom, F on the bottom. So E is equal to H times F. If you cover up h, h is equal to E, this line means divided by F, and so on. Alright, then we've got this formula, C, which means speed of light is equal to frequency times wavelength. If you use this to make a magic triangle, that's what it would look like. Speed of light, again, is also a constant, much the same in a vacuum or in air, 3 times 10 to the power of 8 meters per second. Again, that's a constant, and we will give it to you. So if you take this formula, C is equal to F times the wavelength, frequency times wavelength, and you solve for F, frequency would equal to speed of light divided by the wavelength. Okay, and now if I've got frequency from this formula, if I take that frequency and I combine those formulas together, I'm actually going to get that one. So I'll do the derivation for you over here. E is equal to H times F, but now instead of having frequency, I'm going to replace frequency with speed of light divided by wavelength. So it's equal to H times C over F, and try not C over F, C over lambda. Speed of light divided by the wavelength. And so we can then say that energy is equal to h, Planck's constant, times speed of light over wavelength. And that's then the same as that formula up there. So that's where they come from. It's mixing up this formula with that formula. So if you combine both of those, you're going to get that formula. All right. E is quantum energy measured in joules. Make sure your wavelength is in meters. If we give it to you in nanometers, you're going to get your calculations wrong. H is Planck's constant, and speed of light is also a constant that will give you. Alright, so practice time. Complete the following table. Please make sure that you don't get caught out. Wavelength over here is given to you as nanometers. So we've got green, it's 540 nanometers. Remember, nano means times 10 to the power of minus 9. Alright, you're going to use the F is equal to C over lambda, this formula. You can use that to calculate the frequency. And so if you take on your calculator speed of light, 3 times 10 to the 8, divided by the wavelength of 540 times 10 to the minus 9, you'll get 5,56 times 10 to the 14 hertz. Please do the same for this one and this one. And if you want to calculate wavelength, just want to make a little note here, nanometers. If you want to convert between nanometers and meters, times 10 to the power of minus 9. And meters to nanometers, you're going to have to multiply by 10 to the power of 9. Alright, so for frequency, sorry, if you want to get wavelength, you're going to use wavelength is equal to speed of light divided by the frequency. So this formula over here, just rearranged to get wavelength. And then I'll give you the wavelength for violet and ultraviolet light. Pause the video, do the calculations, and mark it afterwards. Now for the wavelength of violet light, you should have got that it's 409 nanometers. Now remember, it's because the heading at the top of this table said that you must write your answer in nanometers. Your calculator may have told you that you've got 4,09 times 10 to the power of minus 7, but that would be in meters. So if you wanted to convert that to nanometers, you're out by a factor of 2, because here we've got times 10 to the minus 7, and you need to have your answer as times 10 to the minus 9. Okay, that would have been 350 nanometers. So notice here that the wavelength of green light is 540, and the wavelength of UV is 350 nanometers. So if you go to your spectrum over here, so here the green light, it's got a wavelength of 540 times 10 to the minus 9, which means nano. Okay, the border between violet and ultraviolet would be 350 nanometers, or 350 times 10 to the 9 meters. So this is shorter wavelength, that's longer wavelength. If the nano confuses you, times 10 to the minus 9. So 350 shorter wavelength than 540. Okay, so yeah, for this working out, you're going to have C is equal to F lambda, and therefore frequency is equal to C over lambda, but I've already given you those equations. What's the wavelength of a radio wave for 947, the radio station 947, which operates on a frequency of 94.7 megahertz? The station actually used to be called 94.7. So our frequency is 94.7 megahertz. You'll remember from last year that actually that means 94.7 times 10 to the power of 6. Mega, capital M, means times 10 to the 6 hertz. Speed of light is 3 times 10 to the 8 meters per second. There's our formula. Substitution, 3 times 10 to the power of 8 equals to 94.7 times 10 to the 6 times the wavelength. So if you solve for wavelength, you're going to get 3,17. The SI unit for wavelength is the meter. Again, pause the video and complete the rest. I'm going to do it with you now, but please pause the video, and then I'd like you to complete up to and including number 5. So if your cell phone signal has a wavelength of 32,2 centimeters, note that that's not in an SI unit, then what's the frequency of that signal? So you can use C is equal to F times lambda, speed of light 3 times 10 to the 8. Frequency is what we're trying to solve for, and the wavelength is 33,2. But now to convert centimeters to meters, you need to divide by 100. So it's 33,2. Remember, centi is the SI unit for 10 to the minus 2. And then you press buttons on your calculator and you'll come up with the frequency is 9,04 times 10 to the power of 8 hertz. Why are gamma rays considered to be more dangerous than microwaves? So you need to think of it in terms of energy. Frequency and energy are related by this formula. So there's a direct proportion between energy and frequency. Frequency is directly proportional to energy, or energy is directly proportional to frequency. So high frequency, high energy. So now have a look on your spectrum. So the higher frequency tends to be on the right hand side. So if you've got a higher frequency, then you will have higher energy. So gamma rays are more dangerous than microwaves. Here's gamma waves, here's microwaves. Gamma waves are high frequency, whereas microwaves are lower frequency. longer wavelength, lower frequency, as opposed to gamma rays that have got shorter wavelength but higher frequency. So energy is directly proportional to the frequency. So you can say higher frequency means that you've got higher energy. So if you've got more energy, that would make them more dangerous. Also, let's relate it to wavelength. So wavelength is related to penetrating ability. So if you've got gamma rays, they've got a much shorter wavelength. Gamma rays shorter wavelength, whereas microwaves are closer to the longer wavelength side. Gamma rays shorter wavelength. So if you've got a smaller wavelength, you're going to have a greater penetrating ability. And that's why, for example, an X-ray will pass through a subject a lot more than radio waves will. Okay, so that's why gamma rays are considered to be more dangerous than microwaves. If you needed to kill bacteria safely on a surface, explain which type of radiation you'd use and why. You'd use ultraviolet. Gamma can also be used. In fact, in one of the videos, I think they did mention that gamma radiation is used to irradiate chicken eggs to kill the bacteria on chicken eggs, so that when you consume them, they are safe for you to eat because they don't contain bacteria. So you use UV radiation because it's able to kill bacteria, but it's not as dangerous as X-rays or gamma. You may have been to a medical facility, for example, a doctor's room, and maybe they took out an instrument, or even a dentist, they took out a blade or a scalpel or so, and that's been in a box with UV light. That UV light would kill any bacteria on the surface. Alright, your homework, please, before the next lesson, is to complete the rest of this booklet. In the next lesson, we will go through it and mark it, and then I'll give you a worksheet to do on it. Please, after this, make sure you watch the other videos that I will put up onto Teams. Thanks, Gr10s.